this idea in at the point that they're teaching method of characteristics. I'm just sort of following the pedagogy of Shear and Levy on this. If you look, I think back on some prelim problems, you will see ranking Hughes condition comes up from time to time. So good thing to know. All right. So I think we're ready to get back into Green's functions now. Okay. So what we talked about before, we really focused on a 1D boundary value problem. Okay. We'd actually like a much more general framework for the Green's functions. And in particular, we can think about it this way, okay, in terms of boundary value problems. So we're not going to think about time-dependent problems for now, although, there certainly are Green's functions for time-dependent problems. We're going to assume that we have typically some problem with a boundary. You could have an open domain. So some of these ideas actually do work, like, if you have like the half plane or something like that, or outside of the unit ball, okay? But the idea usually is that U, okay, lives in quite sure why I'm writing it like that. Okay, U is some subset of Rn here. Okay, and U, yeah, is going to map U to some R value. Okay, this is my boundary condition here, right? And this is my PDE here, okay? L is my linear operator, okay? And BU is going to be some linear combination, okay, of U and possibly its derivatives, okay? So, for example, you could have a Dirichlet boundary condition, you could have a Neumann boundary condition, you could have mixed boundary conditions in this case, okay? And those are typically the kinds of boundary conditions that we're going to look at, okay? All right. So the question is, can we take this general setup and come up with a solution method, assuming that we can get a fundamental solution to this PD? And what's the fundamental solution? The fundamental solution is going to be defined on the unbounded domain. So the Green's functions methods are really ways of taking fundamental solutions, which are much more straightforward to get because they live on the unbounded plane. You have lots of nice translation and symmetry properties, and sort of pruning them or adding things to them so that they satisfy the boundary conditions that you want. The task here is really to adjust the boundary condition. You assume that you already have a handle on how to solve the PDE. Okay, so fine, so that's the goal. Okay, so how do we get there? So the fundamental solution of the boundary value problem, we call it capital Phi of XY. This is going to satisfy L of Phi XY. And I'm going to go ahead and write like a naked delta, function here, function in quotes. Okay. So sort of abusing my notation from before, right? because we know that a delta function is not really a function, right? But let's just say that we're writing this in the sense of distributions, okay? So really, everything in that equation should be wrapped, in an integral integrated against a test function, okay? So if phi is locally integrable in y for x is living in Rn, okay? And let's say that f lives in the space of test functions, right? So now we're assuming that f is infinitely differentiable, right? Then the following thing is true. V of x is equal to the integral over Rn of phi xy f of y dy is equal to, so now we can write this as just capital phi integrated against f, okay? Or phi acting on f in the sense of distributions, right? Satisfies LV equals f, okay? But specifically on Rn, right? So we're still not tackling the problem of putting this on that domain capital U. We're saying this is true in Rn, okay? So LV of x is equal to L acting on phi f. This is equal to L acting on phi f using the properties of differentiation of distributions, right? We know that L acting on phi is going to give us delta x minus y, okay? And here we'll use our dummy variable as f of y. So this should equal f of x, which is indeed what we want it to equal, okay? So I can, my fundamental solution, I mean, we found this essentially in the case of Poisson's equation, the fundamental solution to Poisson's equation. We can take the fundamental solution to Laplace's equation, integrate it against our inhomogeneity, and that's going to give us our general solution. What we're saying is maybe there's a broader class of PDEs where we can extract that fundamental solution phi. We should always be able to do that. We should always be able to integrate that against our inhomogeneity, and that's our solution, okay? Now, that's fine, okay? We can satisfy the PDE, but of course, the task is now to satisfy the boundary conditions. And we went through this a bit in the one-dimensional case. And the problem really is to find some function that you can add to your fundamental solution that's going to make your boundary condition satisfied, right? So, either remove the non-zero parts or something like that at the boundary or something else, okay? So the idea is to add a solution, W, okay, to this fundamental solution, right? And that would hopefully correct for the boundaries, right? So what we need in that case is some LW equal to 0 such that U equals V plus W. And this is going to satisfy BU is equal to G. Right, that's what we need there. So what does that give us? That gives us that LW equals 0 for x in U, and BW is equal to G minus BV using linearity, right? on the boundary there, okay? So that means that LU is equal to LV plus LW, and that gives us back F, because this is F and this is just 0. BU now is going to be equal to BV plus G minus BV, so that's just equal to G, okay? Well, that's great, okay? So now the task is to solve this. And you might say, well, why the heck are you doing this, in multiple steps? Why not just solve the whole ball of wax in one step? Turns out it's usually easier to get the fundamental solution. Moreover, you can often construct this W from the fundamental solution, okay? And that's essentially the piece that you use to be able to solve this, boundary value problem that we've now pushed our problem to. Okay. Questions about this? We got about 5 minutes left. I think I'll probably have time to maybe set up the general framework, and then we'll jump to maybe Laplace's if we have time. Okay. Okay. So as I was saying, right, we can get a clearer solution or a clear formulation by removing the fundamental solution contribution to the boundary, okay? And essentially we'll use a Green's function, okay, to do this, okay? So bear with me a bit. So essentially we'll define this Green's function G on X, Y, and U. That'll be the closure of U actually. LG XY is going to be equal to delta of X minus Y. BG XY is equal to 0. On the interior and on the boundary, okay? And we'll assume that Y is going to be defined on the closure of U, okay? So then the idea, and we did this in the one-dimensional case, is that this Green's function is going to be your fundamental solution minus this correction. We'll call it phi y of x. And this is like our W that I set up before, right? So L phi y of x equals 0, and then B phi y of x is equal to B phi x y, for x is in U, and for x is in BU, okay? So thus, so now this is where we tie it all together. Instead, we want to define U is equal to V plus W, such that V of x is equal to the integral over U of G x y f of y dy, okay? And our W here is going to satisfy our boundary conditions, okay? Okay. So in the second part, essentially what you do is you say, well, let's split this up into two issues here, right? So I'd rather start with something that's already zeroed out along the boundary, okay? And that would be this piece little phi y, okay, that will help me zero out along the boundary. If I have an inhomogeneous boundary condition, okay, I'll have this additional function that'll help me correct for the inhomogeneous boundary, okay? So, we're kind of splitting things up into three different functions. This capital phi, which is your fundamental solution, right? So big phi is your fundamental solution, right? This little phi y of x basically gives homogeneous boundary, okay? And then w basically if you have an inhomogeneous boundary, okay? And so in most cases, right, you can really only like estimate your Green's function, and you often do that using eigen function expansions of your linear operator. So and that's one thing that's on the homework, right, is this problem where you sort of come up with this eigen function expansion in order to get a Green's function, okay? So estimates of g x, y, right, are made more easily, okay, than necessarily computing u directly, okay? The other thing is once you have a Green's function, right, it doesn't matter, the particular inhomogeneity that you're using, you can integrate against any inhomogeneity. So for numerical methods solving PDEs, you may just want to, compute the Green's function one time and then look at all, these different cases that you run into. Same thing analytically. But in special cases, we can actually find G explicitly. And that's what we'll go through in this class. And this also works for W in this case. And so where we're going with this, I think maybe for the next couple lectures is showing how this works in the case of Laplace